Okay, good morning again. This is Professor David J. De Los Reyes. Okay. Am I at the center? Okay. My next topic will be a long video format discussion on this is alternating current circuit. Uh, this lecture is for those who are planning to take up electrical engineering. Okay, let's proceed. The title of the subject matter for this morning will be Alternating Current Circuit, lesson number 15. This is now lesson number 15, and the title of the topic will be Impedances in parallel, or this is actually a series circuit. No, parallel circuit. But I want to make the title different from simply parallel circuit. It will be impedances in parallel, meaning the loads are connected in parallel and the total load under AC circuit is actually impedance. So I make the title impedances in parallel or simply parallel circuit. Okay, let's try to bring out the figure. The figure for impedances in parallel, the total opposition offered to the flow of alternating current in alternating current circuit is actually impedance. And the connection for this morning will be parallel. Okay? Parallel meaning the voltage across all the impedances are actually equal. If under the so-called series impedances, the current is common, but under parallel impedances, the voltage across the individual impedance is actually equal to E, and that is common for all of them. So the difference between series and parallel is that under series impedances, the current is common, and under parallel impedances, the voltage is common, meaning the voltage across each impedance are all equal, and this is equal to the applied voltage. Parallel connection is actually the real connection in real life, because there is no such thing as series loads. Series loads is just used in the so-called study of maybe simple DC circuit, but under impedances, okay, the real connection is actually parallel connection. That is parallel. All the connections in the wiring in the houses are actually in parallel. We got two lines, so if we try to connect a light to that two lines, so we just stop the two lines over here, and we got a light. So the connection is actually parallel, right? It is something like this. If this is the lighting, we tap it here, we got the lighting. If this is a motor load, we tap it here, okay, the motor will run. Okay, let's try to bring out the derivation of the so-called equations that is needed under parallel impedances. This node here, or this junction, I will call it junction A. If we try to take the summation of the current at junction A, and this should be equal to 0. Sigma notation, capital letter I meaning current, subscript A at the location junction A, and this should be equal to 0. That is actually Kirchhoff's current law. If we try to take the summation of the current here, current entering should be equal to the current leaving. So it should be current entering is plus IT. Current leaving this junction, actually 3. It is actually I1, I2, and I3. Minus I1, minus I2, minus I3, and this should be equal to 0. Okay? If we take the summation of the current here, this I2 here emanates from this I3 here emanates from this, and this I1 here emanates from this. And the current entering this one is the total current coming from the alternating current source. So if plus IT minus I1 minus I2 minus I3, and this should be equal to 0. And if we try to transpose this I1, I2, and I3 to the right hand side, we remove this one. Okay, this should now be equal to I1 plus I2 plus I3. So under parallel circuit, the total current is equal to the summation of the individual current going to the individual branches. So this should be, if C1 here will be the lighting load, I1 will be the total current consumed by this lighting load. If C2 here will be a motor load, assuming it's a motor load, I2 will be the current being consumed by this motor load. And if C3 here will be again a motor load, the total consumption of this motor load will be I3. The meaning of this, I total should be equal to the sum of I1 plus I2 plus I3 with the given condition vectorially. We add it vectorially because the current are actually a complex thing. It got a real part and the so-called imaginary part. So we could not use the addition of real numbers. So our knowledge of the so-called complex numbers will be applied to the solution of a parallel AC circuit. So equation number 1 for parallel circuit, I total will be equal to I1 plus I2 plus I3. It depends on how many loads are connected in parallel. But for this given figure, it will be up to 3. So I total will be equal to I1 plus I2 plus I3. Okay, let's try to bring out on how to compute the total impedance for a parallel impedances. Okay? By definition, voltage is equal to the product of current times impedance under AC circuit. The equivalent of this under DC is actually voltage is equal to IR. Right? Because the only opposition offered to the flow of direct current under DC circuit is just only resistance. But under impedance, total voltage will be equal to the product of current times impedance. In which this impedance here, it got the real part and the so-called imaginary part, and that is R plus Gx of L minus Gx of C. That is for impedance. So if voltage is equal to IC, we will compute for I will now be B over C. And if we try to substitute this B over C back to this equation here, what will come out? The voltage across the load is actually E, right? And the voltage across C1 is still E. So this will be E over C1. And the voltage across C2, okay, will still be equal to the source voltage E. And the voltage across C3 is actually equal to the voltage across this, equal to the voltage of the source. So that is still E. If you try to observe the given the resulting equation after the substitution, this E here are actually same E. Okay, so actually we could cancel. Or just what we call is factor out E on the right hand side, and there's an E on the right hand side, therefore we can cancel. So what will come out after the cancellation will be 1 over C total should be equal to 1 over C1 plus 1 over C2 plus 1 over C3. Then there is an equation under AC circuit that is 1 over C total is actually equal to Y total, and 1 over C1 will be Y1, and 1 over C2 will be Y2, and 1 over C3 will be Y3. And what is Y? Under the study of parallel AC circuit, Y is actually termed to as admittance. Okay? Admittance. If under what they call this series impedances, Z is actually impedance. Impedance, this is synonymous to the word, what they call this, word impede, okay, or obstruct. So these two here are actually reciprocals. Okay? Under AC circuit series, we term Z as impedance, and under parallel circuit, this Y here, we term it as admittance. Admit, you don't fight it out. Impede, you fight it out, right? You try to obstruct. So under the study of parallel circuit, Y should represent admittance. So if we try to replace this substitution here back to this, what will come out will be Y total should be equal to Y1 plus Y2 plus Y3. And the unit is mho. MHO, it is actually ohm in reverse. Right? So for parallel circuit, to compute for Y total, okay, take the reciprocal of the individual impedances, then you add them vectorially. And to compute for the total impedance, you go back here. After computing for Y total, you go back here and you could compute for Z total. So if you now know Z total, you could compute for current and other things. Okay, that's how we work under parallel impedances. That is, Y total is equal to Y1 plus Y2 plus Y3, and the unit is mho. It is actually ohm in reverse, in which Y with the subscript capital letter T is total admittance, Y1 will be admittance number 1, Y2 will be admittance number 2, and Y3 will be admittance number 3. Okay? That's how we compute for the total admittance under parallel circuit, because after the computation of the total admittance, you just take the reciprocal of it and you could compute for the total impedance. And if we know the total impedance, we could compute for the total current drawn by this parallel circuit. Okay? There is another formula that will come out under parallel impedances. That is capital letter Y will be equal to capital letter G plus J B sub C minus G B sub L. And the unit of this is actually mho. If under parallel, what you call this, under series circuit, Z is actually R plus J X sub L minus J X sub C. Okay? This is for series impedances. Under parallel impedances, okay, total admittance will be equal to J plus JB sub C minus GB sub L. And which the value G here, G, as in God, okay, it is termed to as conductance. Why conductance? This is the reciprocal of resistance. Right? Resist. It's the opposite of conduct. So under parallel circuit, parallel impedance, instead of resistance, the real part of the admittance is actually conductance, and the unit is actually mho. The B sub C, it will be the capacitive susceptance. We got another word here, susceptance. Okay? This is the reciprocal of inductance. Okay? It's the reverse of inductance. Right? So B sub C should be capacitive susceptance, and the unit is mho, and B sub L will be inductive susceptance, and the unit is still mho. Okay, so you now know the difference. Under parallel circuit, Y is J B sub plus J B sub C minus J B sub L, but under series circuit, Z is actually R plus J X sub L minus J X sub C. And the formula on how to get the value of the so-called conductance and susceptance. Conductance is the reciprocal of resistance, right? So if you know the resistance, to get the conductance, just take the reciprocal. And the unit is mho. I write this one as the original ohm is like this, right? It's omega. So if we try to take the inverse of this, okay, upside down, this is termed to as mho, read as mho. And B sub C is the reciprocal of X sub C, that is 1 over X sub C. So this is 1, X sub C is actually 1 over 2 pi FC. So this 2 pi FC goes up. So B sub C is actually 2 pi FC. And the unit is mho. Still mho. B sub L, it's the reciprocal of the inductive reactance. We term to as inductive susceptance. So this is 1 over X sub L. X sub L is 2 pi FL. So B sub L is 1 over 2 pi FL and the unit is mho. Okay? So these are the needed equations under the study of parallel impedances. And take note this one, guys. This is the real connection in real life. All our connections in the houses and even in the industry-wise, okay, the connections are in parallel. Meaning to say, you got two lines here, so to make a load alive, just stop your load over here. And that connection is actually parallel. Okay? You keep on tapping, that's why the connection is parallel. Okay? You got two lines, you tap your load, okay, you could consume current. You tap another load, you could consume any current. So the connection is actually parallel. So in real life, the real connection is actually parallel connection. Series connection, I think that is only just used maybe in the study of physics, in the series parallel connection of batteries. But under AC circuit, the real connection is actually parallel connection. Okay, so for those of you who are studying AC circuit, this is for you guys. If you want to subscribe to my channel is at youtube.com/@ProofTVJ. If you want to share it, please click share. Try to watch my long video format videos. You will learn something from it. Okay, good morning from Los Angeles. Professor Impedances.